Why did the circuit go to therapy? It had a lot of resistance to change. What did the resistor say to the capacitor? You're always charging me up. Why did the engineer break up with his girlfriend? Because he realized he was in a short circuit. What do you call a group of wires? A bundle of connections. Why did the circuit get kicked out of the party? Because it was always short circuiting. Uh, Hi everyone. Circuits are the nervous systems of electronics. Just like blood flows in veins, current flows in wires. Today, we'll study the basics of circuit and network theory. So let's take an example. Let's say we have V which is equal to 10 volt. We have R which is equal to 5 ohms. And then we have current which is equal to 2 amps, right? So our voltage here would basically be 5 into 2, right? Which is equal to 10, which is what we have over here. R1, R2, R1, 3, R4. So let's say we have uh, two circuits. So this is basically a series type of circuit, and this is a parallel, right? So in a series circuit, our resistance will add up. So a resistance is basically in a sequential fashion, whereas in a parallel circuit, we have resistance that is in parallel to each other. So R3 and R4 are in parallel to each other, right? So this is a parallel circuit. So in series, resistance add up. In parallel, reciprocals add. So for example, if you want to calculate the total resistance in a series circuit, that would basically be R1 plus R2, right? And let's say R1 is 10 ohms and R2 is 20 ohms. Hence, our total series would be 30 ohms, right? Now, if you want to calculate the parallel resistance, right? Similarly, let's say if R3 is 10 ohms and R4 is 20 ohms. So in parallel, we have uh, the reciprocals that are added. So 1 upon R1 plus 1 upon R2, which is equal to 1 upon 10 plus 1 upon 20. So this basically evaluates to zero point 0.1 plus 0.05 is this 0.05 is basically going to be 0.15 ohms. So I hope this is clear. So moving on to the next topic, we have the let's say we have our battery. plus, and have this. Now let's say we have this as resistance R1, R2, and R3. And let's say we have a voltage source as Vs. This is basically our voltage source. So now this is the loop, and we have current flowing, which is I in the circuit. Current always flows from positive to negative. Just remember that. So we need to remember that this Kirchhoff's current law, or KCL, right? Kirchhoff's current law, or KCL, states that the sum of currents at a junction is always zero. So at a particular junction, our sum of currents will always be zero. And in KVL, which is Kirchhoff's uh, voltage law, the sum of voltages in a loop is always zero. So what this means is, for example, we have, let's say we take this junction, right? Let's say we take this junction. Let's say this is I1, this is I2, and this is I3, right? Now, Kirchhoff's current law states that I1 will always be equal to I2 plus I3. Why is this? Because the current leaving from a junction, I1, should always be equal to the sum of the currents that are entering the junction. So here, I2 plus I3 is the current that is entering the junction, and I1 is the current that is leaving. Hence, we have this equation for KCL. Now, let's say we want to talk about KVL, or the Kirchhoff's voltage law, right? Now, what would that mean? That would basically mean that the sum of all the voltage drops around the loop is equal to zero. And this means that let's say we name this as A, let's say this is B, this is C, and let's say this is D, right? So we can say that VAB plus VBC plus VCD plus VDA is equal to zero. So all of the voltage drops across any given resistance is always equal to zero in a loop. That is the Kirchhoff's voltage law. Now let's move on to the next topic, which is network theorems. So in this we have two primarily like two theorems. So first is uh, the Thevenin, and then we have the Norton. theorem. So let's say we talk about the first theorem, which is Thevenin, right? So Thevenin theorem states that it is possible to simplify any linear circuit, irrespective of how complex it is, to an equivalent circuit with a single voltage source and a series resistance. So what this means is, let's say we have a complex linear network. So let's say we have a network containing many R's or resistance and voltage sources. So all of this, right? Like let's say we're measuring this across a resistance R. This can be simplified to a single linear circuit with a single voltage source, which is V, Vs, and we have R, Rs, C, this is B, have RL. Yeah, so this is what we have for the Thevenin theorem. So a single voltage source, a single resistance, Rs, and this is the RL. Now let's move on to the next theorem, which is the Norton's theorem. So what does Norton's theorem state? So Norton's theorem states that any linear circuit can be simplified to an equivalent circuit. So what this means is, for example, let's say we have our current source, which is I Norton, right? And let's say we have our resistances. So let's say we have R Norton, and we have our load. So now let's say we want to, so now our Norton equivalent circuit. So our equivalent circuit would basically reduce down to this. So just a current source and a single Norton resistance. So all of this gets compressed into the single circuit. So this is what is called as Norton's theorem in circuit analysis. So now recap and use. Learned law, series parallel, Kirchhoff's laws, and theorems. Next, we'll delve into basic electronics. Thank you.